All right, ladies and gentlemen. So finally, we are at the very last lecture and discussion of the conference. So we are going to go from h bar equal to 0 back to h bar not being equal to 0. And we have a lecture by Artur, who is the director for the Center for Quantum Technologies here at NUS, to be telling us about Feynman, quantum computers, quantum weirdness, and other topics.
Thank you very much. It's a great pleasure to be here. And I have to say up front that I never had a chance to meet Richard Feynman, but I think he had an amazing impact on my life. I don't think I would ever be doing physics if not for his lectures on physics. At some point, I don't remember when was it, I was probably in primary school, when my mother bought me those 3 volumes of, actually 6, because it was in Polish edition. I was reading this in Polish, and in Polish translation there were, I think, 6 volumes. It was like, you know, almost an intellectual transformation. Somehow, for the first time, I realized that physics and the way talking about physics, and most difficult even bits and pieces of physics, can be done in such a clear and such a persuasive, such entertaining way. So I later on, I was always encouraged to look at, you know, whatever Feynman did. I thought, well, you know, this must be a fantastic thing to do. So today I'm going to tell you about his impact on the field that is actually quite popular today, and that is quantum information science. And it all probably goes to a paper. Well, there are a few papers that Feynman wrote about computation, but one particular paper that probably has the most significant impact on the field as we see it today was the paper that was actually a summary of his talk that he gave in 1981 at MIT at the first conference on physics of computation. So this paper is interesting from all kind of different perspectives, but basically, the paper was about simulating physics with computers. And then Feynman asked this, the question, is it possible to always to simulate whatever physical process you pick up with a computer? And then, of course, physics enters to this, because then the question is, okay, well, what about quantum physics? And can you take a classical computer and use it effectively to simulate any quantum phenomena that you find out there? Well, the answer is yes. It's always possible to do it, but the question is, it's not always efficient. And what is remarkable about this paper is that Feynman, for the first time, introduces something that physicists usually don't think about it. Physicists are usually interested in questions like whether something can happen or not, whether the laws of physics allows this to happen or not, right? But computer scientists computer science is also interested in the question, can something be computed or not? But they also learn to ask more subtle questions like, okay, you can compute such and such function, or you can solve such and such problem, but what is the use of physical resources in the process of solving this problem? Do you know efficient way of doing this? So it's not only the question, can you do it or not, but how good are you at doing this? How efficient it is? And in this paper, Feynman touched up on something that we today refer as computational complexity. There are many other, if you read this paper, and I think it's still a very interesting paper to read, there are many other interesting ideas. So he talks about the concept of negative probabilities. He touches up on Bell inequalities without calling them Bell inequalities. what I like, one thing that I find fascinating about this paper is his ability to take something that looks like an obstacle and turn it into a opportunity. So, for example, once you realize that it's very difficult to simulate a quantum system using classical computers, then if you're a pessimist, if the glass is always half empty for you, you will say, oh, well, tough luck, right? But not for Feynman, He says, well, okay, well, if it is difficult, so how about taking this physical process, this quantum process, it goes click, 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 click in real time, and see this as a computer. So you turn the table. So, okay, well, maybe then doing it this way will generate something that is a very powerful way of computing. Then another thing that Feynman, talking about the way of simulating quantum physics with classical computers, another thing he goes into is the notion of quantum entanglement, and says, in some cases, certain things are basically weird in a way that it looks like outcomes of measurements do not have predetermined values. So that's my sort of free interpretation of what he says in the paper. And therefore, you cannot, generate this by classical simulation, because by nature, whenever you have classical simulation, you have values associated with just about everything you compute on. And there are quantum phenomena that, having this approach, read hidden variables, that doesn't actually generate exactly what we see. So again, Feynman didn't go any further than that, but maybe I had a good fortune later just to look at it from the perspective of, well, maybe it is also good for something, and maybe the fact that values do not, that certain outcomes do not have pre-existing values until you measure them, perhaps you can use it for secure communication. So I would like to take you through the basic of quantum computation, because I think that the way quantum computing is perceived today can be traced to this paper. There, of course, an open question whether Feynman ever realized how powerful quantum computers can be, and there were truly remarkable contributions that shaped the field later on, especially by David Deutsch, who defined the concept of quantum Turing machine and quantum computation. But I think that when it comes to computational complexity or efficiency of computation, pretty much everyone agrees that this paper really started the field. So what I'm going to do in my talk is going to be a very simple talk, and really, it can go any way you want. So if you feel free to interrupt me at any point, and I'm happy to discuss something else if you don't like what I'm talking about. But my original plan is to give you some very simple introduction to quantum computing and try to sort of show where is the power of quantum computation coming from, and then maybe say a few words about the last point about quantum crypto. So let's see how it goes. So let me start with probabilities, and because I would like to then take the view that quantum physics is basically a new kind of probability theory. But before I try to persuade you that there's no issue about H bar and let me just start with the probability theory. The notion and concept of probabilities, the whole thing has a long history. Basically, maybe the first person who really thought seriously about probabilities and tried to quantify was Girolamo Cardano, an Italian scholar, well, what today is Italy, living mostly in Bologna and Milan. And he did it in 16th century, like a century before the French mathematicians started even thinking about it. And over time, the notion of what exactly is probability and how to define probability was always something that was a big problem for mathematicians, mostly because of circular definition. For example, Laplace definition of probability is that, what you do, you look at all possible events and just pick up those that are favorable to a given outcome and take the ratio. But there's a tacit assumption there that all those events are equally probable, they're equally likely. Only this, it makes sense. So you introduce probability by referring to the notion of equally likely, so it's circular. And then, there are a few other people in the history of probability who try to think about it as in all kind of way. But then it really became a serious mathematical topic when Kolmogorov basically took a very mathematical view. He said, I don't care what it is, Probability is what satisfies my axioms. So basically, he introduced a concept of, call it a measure, but basically, you define a sort of a set of events, and you say, well, here are the three axioms of Kolmogorov. And so the first two are kind of obvious. It's a non-negative number, and then probability that something happens is equal to 1. But the third one is interesting, and we are going to look at it more closely in a moment. So the third one says that if something can happen in mutually exclusive ways, then you should add probabilities corresponding to those ways considered separately. So the probability of mutually exclusive events add up. So that's a very sensible axiom. And the thing is, though, the probability theory is, you can look at it mathematically, is about attributing numbers and then playing with them in such a way that is sort of logically consistent. And as long as those numbers satisfy those axioms, then you can derive probabilities of more and more complex events. And you apply this into just about many things. The probability is a very useful concept in real life, in risk analysis, risk assessment, opinion polls, statistical physics analysis, you name it. There are many, a zillions of areas where the notion and the concept of probability is very important. But somehow, you may develop this notion. It's so universal, so ubiquitous that it should be applied just to about everything. But that doesn't necessarily be the case, because nature doesn't really know about it. The Kolmogorov just formulated a mathematical theory of probability, and that's it. And but if you just take what you probably, most of you who were exposed to quantum physics probably saw this double slit experiment, and that it really shows that nature doesn't know about additivity axiom. Nobody told nature that you should add probabilities of mutually exclusive events. And it is indeed the case if you take this iconic experiment that you have a source that and you have a screen with two slits and let's say a screen here, then the probability that you end up somewhere on the screen, say here, is equal to the probability that your photon, or it could be electron, could be neutron, you just name it, takes this path and ends up here with probability P1. And otherwise, it can also take this path. And it looks, that clearly those things are mutually exclusive, because if it goes this way, it doesn't go this way, and vice versa. So you add up probabilities there. But you take experiments such as as this one, and you realize that this is unfortunately not the case, or fortunately not the case. I think my equations are a little bit. Anyway, so let me just talk you through this. It turns out that the nature works in a different way, and there was then a need to modify the theory of probability by saying that, by introducing complex numbers, calling them probability amplitudes, and saying, well, there is underlying structure to probability. You have to, in order to get probability, you have to take mod square. But when it comes to additivity axiom, you just apply this to probability amplitudes, not to probabilities. So you have to add probability amplitudes for mutually exclusive phenomena. So in other words, if something can happen in few mutually exclusive ways, you add probability amplitudes and then take mod square and then you get the probability for your event. You know, it is the way, you know, it's a good way of doing probabilities, but when you start working on probabilities this way, you quickly discover that indeed in this, say, double slit experiment, you take the probability amplitude alpha 1 that the photon goes this way, add it to this probability amplitude that photon will go this way. So you have alpha 1 plus alpha 2, take mod square, and then you have indeed probability P1 and P2, so that is mod alpha 1 squared and mod alpha 2 squared. But you also have this extra term. And you so this is the classical part. So this is where, you know, Kolmogorov axiom applies. So this is what classical probability would tell you. But this extra part is a truly quantum addition to the whole story. So basically, you know, if you want to be very simplistic and at purely instrumental level, you can say all there is to study quantum physics is to, you know, to study those interference terms that appear in many experiments when you add probability amplitudes rather than probabilities. So the new thing when you introduce quantum physics is this extra term. And if you look at this extra term, you know, mathematics is trivial, right? But what is interesting is a physical interpretation here, or a little bit of, you know, looking at this would tell you, first thing you notice is this can be either positive or negative, right? This cos can go from -1 to +1. So that means that with respect to the classical result, your probability can be either lower, we call destructive interference, or enhanced, and that would be constructive interference. So depending on the sign of this term. Another thing you may notice is that this extra term really depends on the difference between the phase settings between those two paths. And this is actually quite surprising because somehow this particle that goes from the source to the screen has to experience both in order to know about the difference. So how the hell does it react to the difference? Why it doesn't react to phi 1 and phi 2? It reacts to the difference between the two. So how does it know about the difference? Well, I don't know how it doesn't know about the difference, but it somehow sniffs the two paths at the same time. So some mathematicians who are confused about this, they try to defend Kolmogorov and say, well, you know, maybe those two events are not mutually exclusive, because if it reacts to the difference in phase settings, obviously it had some kind of knowledge of those two paths, and maybe in some weird way it goes through both paths at the same time. So maybe I'm not going to. I promised to myself to put this lecture on purely instrumental level, so I'm not going to go into interpretations and so on and so forth. But this is something obviously to think about. Now, so don't worry. This is actually crucial for understanding quantum computing, and you'll see where I'm going perhaps by saying that there is a quantum interference and there's this sort of extra term. In a moment, I will be telling you that quantum computers are complicated quantum interferometers, where you can enhance probabilities of correct answers, and you can actually reduce probability of wrong answers to computation. And all you do is just play with these interference terms. But so this is actually a spoiler. Now you can fall asleep for 10 minutes. But let me just continue with this more systematic way of introducing this interference. So, you know, the word is indeed different. You may think that indeed somehow this particle goes through those two different slits, this way or another. And you know, you can experiment with this simple interference that I just described, not only in double slit experiments, but you can also build devices where you control those phases. So physicists can do it with photons. You can build, say, a Mach-Zehnder interferometer where you put, you can control phi 1 and phi 2 in these experiments. You can do cavity QED, beautiful experiments where the interference goes in internal states of the atom. You throw atoms through cavities, and the atoms go through the cavity and go through, say, 3 different zones, like in the Ramsey interferometry, where in one zone, the first one, for example, here is say, well, actually this one, the green one, the atom goes from the ground state into the superposition of somewhere in between 0 and 1, or ground state and excited state. And then it just experienced some kind of a phase shift due to some off-resonant interactions in between those Ramsey zones, and goes through another Ramsey zone, and then the state of the atom is detected. And whether it is in the ground state or excited state really depends on the phase shift that accumulated during the transit between the Ramsey zones. Another beautiful set of experiments of quantum interference is based on trap ions. So where you send a resonant pulse, you prepare a superposition of your ion in a trap, let it evolve, send another pulse, and check the state. So what is interesting in those experiments, that basically where your system ends up crucially depends on this phase. The phase is the significant thing here, or the phase difference to be precise. If you can control it, then you can play with it, like in those experiments. And those experiments, so this, for example, is experiment that was performed in École Normale in Superior in group of Serge Haroche, and this was from Dave Wineland experiments in Boulder. So those experiments were so beautiful that people eventually got Nobel Prizes for them. Sometimes, there are phenomena where those phases cannot be really controlled, but we know, for example, that the systems are very sensitive to, if you immerse a system in, say, gravitational field, and you do neutron interferometry, then you can pick up phases due to the fact that the two paths may be at different heights, for example. And so this makes those kind of devices good as sensors. If your phase is very sensitive to some physical effect, so that means building interferometer and introducing phase this way, you have a very sensitive device for whatever, magnetometer, gravitometer, you name it. So this quantum interference uses is quite ubiquitous today. But what is even more interesting is not just a single particle quantum interference, because that one is kind of still open to all kinds of different interpretations. What is really truly interesting and much more difficult perhaps to understand in all details is a quantum interference, but involving many particles, multiparticle quantum interference. So for example, you can take those ion traps and make them interact. So what you can see here, I'll say 3 ions. And all those boxes that I put online, so time goes, say, from left to the right, and those boxes represent some elementary interactions. So for example, here you can say a pulse of a specific duration goes onto this ion, and the second ion is affected by the same pulse, and the third one. And then you make those 2 ions interact, and you introduce some phase shift, and those 2 interact, and so on and so forth. So you can actually think about taking ions and introducing a sequence of operations on them. You don't have to give them any logical mathematical meaning, but you can as well. So we will be interested in situations where you take those ions, identify 2 states, and call them quantum bits. So the one state would be called 0, the other one would be called 1. And those, we can pick up some operations that are easy to perform, and we call them quantum logic gates, because that would be like a phase shift of a certain type. It could be a pi by 2 pulse. It could be exchange interactions between those ions. You name it. Actually, it turns out that you don't have to pick up so many of them. You can just produce any unitary, any operation, any dynamics of your choice can be induced by very few operations of your choice. So it's a little bit like, any Boolean functions can be computed with operations like AND and NOT and the like. Okay, so this, in fact, when you take such a system of 3 ions, introduces quite an interesting quantum interference in the state space of all those 3 ions. So if you have like 3 qubits, each of them having 2 systems, so the composed system of 3 of them would have 2 times 2 times 2, so there's 8 different systems, and you can just mark them as a configuration of your 3-qubit ion trap or whatever you want to call it. And you may start in some initial state, and each operation here would generate in this state space, configuration space, a certain path taking you from your designated input into different possible outputs. And of course, I only here sketched 2 different paths, but that could be many of them. In fact, there are always many of them. And we will be then taking the system from the input to a certain output, and the system can just follow different possible paths, and you associate probability amplitude with each path, and you start adding those probability amplitudes. So what is it good? So from using this kind of terminology, you can think about 3 different types of computation. You can think about regular deterministic computation. You have a computing machine, you specify all possible states of this machine, and you say, okay, a deterministic computation is simply starting in a given initial state, and by a sequence of logical operation taking it to some final state called the output. Then you can also do probabilistic computation, where you start with your input, and by a sequence of operations you end up with possibly different outputs. But if you want to know what is the probability that you see a given output, then you look at the different computational paths, you look at the probabilities, you follow Kolmogorov axiom, you add probabilities corresponding to all possible paths that start in the input and end up in the same output, right? So that's your probabilistic computation. And doing computation in this particular way can be more powerful. There are some good randomized algorithms. For example, let's say you want to estimate very quickly a volume of a certain object or a surface area. You have this unit square and the green object here. You want to know roughly what is the area. And one way to do it is just to throw randomly number of points and see how many of them will just end up in the green area, and take the ratio of the number you thrown to those that ended up in the green area, and that should be roughly the volume, the ratio, the surface area. And there are many other examples I can talk about. The domino tiling is one of them, but that's just only to say that even though at the very fundamental level, computer scientists are still not sure whether probabilistic computation and randomized algorithms are more powerful, inherently more powerful than the deterministic one, but at least it's clear that there are many practical algorithms that we use that are very good and very efficient. You use all kinds of Monte Carlo methods, and they seem to be working quite well. So you may say, okay, we added randomness to the process of computation, and we have probabilistic computation, and certain problems can be solved in a more efficient way. Now, quantum computation, as you can see, is just one step forward. Say, okay, if we can run the computation on a machine that respects all the superposition and coherence and so on, that can behave in a quantum way, we don't add up probabilities, we add up probability amplitudes. But then the reason then quantum computing can be potentially more powerful is because this extra term that we have here. So you can see that this P1 plus P2 is just like a classical probabilistic computation. And then this extra term here, the interference term coming from those 2 different computing paths, give you a possibility to amplify this output if you want to have constructive interference on those paths, or actually diminish the probability that this will happen. So as long as you can construct your quantum algorithm in a clever way, as long as you can play with the phases, phi 1 and phi 2 in this particular case, you have an extra handle to control. So you can see that it goes one step above probabilistic computation. So therefore, it's not unreasonable to expect that this can be something that can give you better results. You can achieve something. You can construct inherently quantum algorithms by playing with this phase difference on those computational paths. So this is exactly where the extra power of quantum computation comes from. So, and of course, again, I just showed here two different computational paths, but in real quantum algorithms, and you start with the input, and it just goes to all possible states that you can use in this case, and you look at all possible paths, and there are exponentially many of them, starting with a given output, going to a given input, going to a given output, and some of them will just interfere in a constructive way, and some of them will interfere in a destructive way. So this is actually if you really want to have a very simplistic but pretty accurate description of quantum computation, that's pretty much what it is. Now, at this point you may ask, okay, but how do we quantify the power? You say that quantum computers are more powerful than classical computers. What does it mean? And this was actually something that Feynman managed to capture by his intuition very nicely in this paper. Computer scientists have more precise way of defining what kind of problems are considered easy or difficult. And the way it's basically done is by taking an algorithm, doesn't matter whether it's quantum or classical randomized, take a way of solving a problem. So an algorithm should give you a prescription how to solve the problem for different instances of the problem. So for example, if you have a multiplication algorithm, then it will tell you how to multiply two one-digit numbers, to three-digit number, to five-digit number, to 42-digit numbers, right? So it works for any size of the input. So what you do in order to make assessment whether your method of solving, whether your algorithm is efficient or not, you simply apply the same algorithm for different sizes of the input. And you look how it scales. So you increase the input size. So here is the input size, number of bits needed to specify your input. And you look at the execution time and how it grows in time. So it grows as a function of the size of the input. So if it grows like any polynomial function of the size of the input, that's okay. That the computer scientists would say this is an efficient algorithm. Of course, ideally, you would like to have something like logarithmic growth. Those are very efficient algorithms, or linear. You don't like necessarily something that goes like the power of 42 or something, because it may not be the most efficient way of doing it. But still, it means that as we keep increasing the size of the input, you can still do it, and the computer will just stop and deliver the answer in a reasonable time. However, if the execution time grows as the exponential function of the size of the input, that's pretty bad. Then you basically say that, okay, for small instances you may be able to solve the problem, and we know how to do it, but for all practical purposes, this kind of algorithm is not efficient. So the basic separation is between anything that takes polynomial number of physical resources, like say time or number of computational steps, versus exponential. And exponential is, it really grows fast. I don't know how many of you really have we don't have sometimes good feeling how fast it is, but it is extremely, extremely fast. If you take anything and start doubling it, very quickly the number you get is insane, right? It looks very innocuous at first, this exponential growth. For example, take the piece of paper, right? So let me ask you a question. How many times do you think you can fold this paper? What would you say? So 10? So, just once, twice, 3, 4, 5, 6, maybe I can do 7. But this is because I'm just running off the surface area. So it still looks like a doable thing. But say, take a roll of a toilet paper. How many times you think would be able to fold it this way? So you just half and then again and again. 8? take the roll, as long as you want, so that you don't run out of the surface area. Just take a roll of a toilet paper of the size of, I don't know, a few kilometers. How many times do you think you'll be able to fold it? I wouldn't know it, but so I give you like a bet. If you can, whoever can do it. You said what was the world record? 11 times. Okay. Well, I was about to offer a bet that if you can do it in, say, 10 times, then I'll just pay you $100 or $1,000. So maybe that would be more motivational. So anyways, okay. So let me just make this offer to any one of you. So whoever actually can demonstrate that you can fold a toilet paper of any length more than, say, 10 times, I'll happy to part with $1,000. Just send me a video and I'll trust you. So, but I think that you can estimate, to fold it n times, it would go take the sort of the thickness. What do you think would be the thickness? How would the thickness grow? So this is another interesting problem, right? So how would the thickness grow? So if it goes roughly like what? If after n folding would be like 2 to the n roughly, right? And so if the thickness is like 0.1 millimeter, I don't know what it would be. So it would go, well, you can easily try to estimate what is it, say 2 to the power 40 times 0.1 millimeter. If you have a calculator, you can work it out and compare it to the distance of the moon or whatever. Not to mention other interesting problems, right? For example, one may wonder, how much energy would it cost you to fold it, At the very beginning, it's quite easy, but keep on folding, and at 42, I don't think you'll be able to do that. But give it a try, and remember, 1,000 Singapore dollars, or for anyone who can send me a video that you can actually do it more than up to 10 times. If you can do it 10 times, you have my $1,000. But it's just what I want to say is that the exponential increase is immense. So it's not surprising that for computer scientists, this is really a separation. Exponential, tough, and difficult. And anything else, like polynomial, is good. So, okay, so we have this scaling. And of course, then you can put problems into, I will explain all those other classes in a moment. But then you can say, okay, for example, we say, let me just go back. So the computer scientists basically divided problems into easy, and they say, if the use of physical resources like time grows only as a polynomial function of the size of the input, it's class P. Those problems are kind of easy. But it is outside P is exponential. Those problems are difficult. There's an interesting class in between. There are some problems, that you find difficult to solve directly. They're exponentially hard. But once you have the solution, you can at least check in polynomial time that the solution is correct. So those problems are called NP problems. It doesn't stand for non-polynomial. It's just for some historical reason it stands for non-deterministic polynomial. Never mind. But NP, for example, factoring is an NP problem because it's very difficult to find prime factors of a big number. So in fact, if I ask you for a prime factor of, say, 15, you say immediately 3 times 5. Right. And I keep on increasing the size of the number, and you will find it increasingly, exponentially more and more difficult to give me the answer. So it is a tough problem. But once, there's a huge number that you want to factor, and somehow you manage to do it, and you give those prime factors to me, I can easily check whether the answer is correct, because multiplication is the operation you use for checking, and multiplication is easy because multiplication is in P. So, there are problems that are difficult, but at least it's easy to verify that the solution is correct. Some problems are so difficult that even verifying the solution is as difficult as solving the problem in the first time. And then the question is, when we talk about the complexity classes, then we may say, okay, with respect to which particular way of computing. And introduction, of quantum computers introduce. You may ask the following question. So, okay, given a problem in P, is this problem difficult for both classical deterministic, probabilistic, or quantum computers? And the answer is that, well, some problems that are difficult for deterministic computer might be easy for probabilistic computer, and some problems that are difficult for even probabilistic computers might be easy for quantum computers. So we introduced basically two extra classes, a class BPP that stands for bounded polynomial, and BQP. So BPP is a class of problems that randomized algorithms find easy. So it takes polynomial use of resources. And BQP is a class of problems that quantum computers find easy. So for example, you take factoring. Factoring is outside P. I was telling you that no classical method of factoring large integers that is efficient is known to us. It's even outside BPP, so there are no randomized algorithms for doing this. But we know that is in class BQP because quantum computers can do it efficiently once we build a quantum computer, of course. So somehow, introduction of quantum computation changed those complexity classes. And this is fascinating because some of those problems are important. The factoring, for example, is behind many methods of encryption that we use today. And being able to factor in polynomial time means that some of the methods that you use on a daily basis without realizing will not be secure anymore. Next time you make a payment on internet, in the age of quantum computing, that wouldn't be considered safe. So, of course, there are also problems that are which we think are difficult for even quantum computers. So it doesn't necessarily mean that quantum computation can solve all problems that are difficult. In fact, there are lots of problems interesting problems that we think quantum computers cannot solve in any better way than classical computers. But this is something that is fascinating for computer scientists because you see the way complexity classes are defined, they are defined regardless the underlying method of computation. Quite often people misunderstand it and say, well, how about I build more powerful machine, like I increase the speed of my clock in my computer by a factor of 1,000,000. Would it make difficult problem easy? Not really, right? The 1,000,000 of course, it will just allow you to solve maybe slightly more, increase the size of the input a little bit more, but it doesn't affect the scaling. What is exponential remains exponential. It just multiplied by a factor 1/1,000,000 in front of it. And whatever is polynomial will stay polynomial. So there's no way of taking a problem and making it kind of easy by improving technology in a very straightforward way. That doesn't work. In order to make problem easy, you have to use some creativity, ingenuity, find an algorithm, find an algorithm and make it polynomial, make it easy. Then you may say, hey, wait a minute, quantum computers, in what way they enhance creativity? No, they don't, but the reason quantum computing gives you a possibility of taking a difficult problem and making it easy is because a different set of instructions, that means quantum computers can operate on those probability amplitudes, and certain instructions that you give to quantum computers do not make sense to any classical computer. For example, you may say to a quantum computer, now take a superposition of number 0 and 42. Classical computer doesn't know anything about that kind of notion, but quantum computer does. And it is exactly because you have a new set of instructions, you can use this set of instructions to construct new algorithms. So the new algorithm is produced by the set of new tools that you are given. Well, why don't we have quantum computers? Well, the reason is, this extra thing that we have, this quantum interference, this interference term, this that allows us to either enhance or suppress probabilities with respect to classical predictions is very, very sensitive to any interference, especially with the environment. So this process is known as decoherence, and effectively it kills this interference term because the noise just messes it up. So you may think about it that there's a jitter in the phase, and the phase difference, jitters very rapidly going from -1 to +1. So I mean the cost goes from +1 to -1 and kind of averages to 0 in this particular case. It's just not quite correct, but one way of thinking about it. Now we can talk about decoherence if you want later on. So is there a way around decoherence? Is there a way to build stable devices like quantum computers? The answer is yes. And let me use a little bit of this sort of analogy from architecture. If you look at the sort of Greek temples, for example, you may see that they are kind of beautiful, but from the architectural point of view, from the engineering point of view, those are very lousy buildings. Why? Because Greeks had no idea how to cover a large area with vault. So they had no concept of arch, no concept of vault. So basically the buildings, you had like 2 pillars and you put a piece of stone and another piece of stone, and it's very aesthetic. It's very, very nice. I mean, it's beautiful, and those Greek temples are truly beautiful. But when you go inside, and there are lots of columns that they have to support, you feel a little bit claustrophobic, except few areas. And it's only Etruscans that introduced arch, and the Romans. So if you compare Greek architecture with the Roman architecture, for example, you see. From the engineering point of view, it's an amazing transition because you go from those areas where are sort of covered with a forest of pillars and columns into areas where you have a vault, you have a big public space that can be covered. But that's not so trivial. If you think about it, how to build an arch, how do you go? You just start piling up those stones, and you have to come to this crucial point, to the keystone, right, to just stabilize the whole construction. Because if you don't go there, it'll just fall down. So this is pretty much where we are as far as sort of as quantum computing is concerned. You can think about the basic blocks, those quantum logic gates that I was telling you about as bricks that you can use. So you have bricks, okay. You want to have good quality bricks, right? So if you have a lousy bricks, your building will just fall apart. So the next thing you do is you put them into a wall and you start piling them up. But in order to build something, to scale it up, you need to make this arch. You have to go to the point where there's something that is called a threshold theorem of quantum error correction, that you have to have a certain level of complexity before you can start scaling this up. And we are not quite there yet, but that's the idea is that we know how to construct those arches, and we also know how to construct those vaults. If we can have a good set of bricks, and we hopefully will be able to do it, it's just a question of the quality of our building material, and hopefully we can build beautiful structures of that kind. So that's how exactly you can, but I don't give you any good answer how the future quantum computer will look like. As far as we know, there's no reason why we shouldn't be able to build a quantum computer. We have a pretty good idea where there is where the problems are and how to solve them. Which particular technology, being ion trap, NV centers in diamonds, superconductors, it's not entirely clear. They all have pros and cons. But eventually, I'm sure there will be a quantum computer. But sometimes as a physicist interested in more fundamental physics than engineering, I wish that didn't happen. I wish there would be, it would be great. Absolutely, the best scenario for quantum computing is to discover something that is so fundamental that says there's no way you can build a quantum computer, because at this point you discover something profound about nature, right? It's much more interesting than building a quantum computer. Absolutely much more interesting. So if we can discover a good way, a fundamental reason for not building quantum computer, that would be the best possible outcome. Absolutely the best. And then, of course, when we discover this new thing, then we will have a new toy to play with. Then we can think about post-quantum computers, use this phenomena that prevent you from building quantum computer for the purpose of computation. So this way or another, that would be fascinating. So that more or less is sort of the first part of what I consider as a Feynman's legacy, picking up on computational complexity in this paper. And I took you sort of, from 81 till today, where we have much better understanding. But I think Feynman was the first one who actually saw that basically doing things in a quantum way is much more efficient. It can be even exponentially more efficient in some cases. And that was a great insight. He couldn't, of course, at that time it was difficult to invent, the whole field, and many people contributed later, discovering algorithm and the way of doing quantum computation this way or another. But I think he was the first one who really realized that there's a potential in this. And another thing that I'm going to mention briefly was another topic that he mentioned in the paper, and that was he was a little bit puzzled with a notion of what we know today as a kind of Bell inequality. But let me just let me skip this and let me ask this question. So suppose I want to ask the following question: is it always the case that a photon has a predetermined polarization? You know what the polarization is, right? So you can measure it, and you know that you pick up a direction of your analyzer, and with respect of this particular direction, you have a binary outcome, +1 or -1 in the units of h bar or whatever. And the question is it always the case that we can attribute the numerical values +1 or -1 to the polarization of the photon? So for this, I want to consider the following thought experiment. So imagine that, and let me just put it in a little bit of adversarial scenario. We have now 3 individuals here, Alice, Bob, and Eve. Alice and Bob are 2 good physicists who are miles from each other, and Eve stands for eavesdropper in cryptographic scenario and could be an evil person. So there is a possibility now. So this Eve provides Alice and Bob with photons. So 1 photon goes to Alice and 1 photon goes to Bob. And Alice and Bob can do whatever they want with those photons. And they're going to measure them. And they're going to choose randomly and independently from each other which type of polarization they're going to measure. So Alice is going to measure either polarization A1 or A2. So 2 different directions, A1, A2. Think about A1 and A2 as binary random variables. So with answers, +1 or -1. So A1 can be equal to +1 or -1. A2 can be equal to A1 or A2 can be equal to +1 or -1. And the same for Bob. So B1 and B2 correspond to 2 different directions. You measure polarization along those directions and you get a binary outcome, +1 or -1. So now, suppose Alice and Bob want to see whether it is possible to satisfy the following criterion. They would like to see whether it is at all possible to have a situation where if Alice measures A1 and Bob measures B1, they get identical result. So +1 or -1. So those 2 random variables are perfectly correlated. The same for B1 and A2, the same for A2 and B2. However, we always want, whenever the B2 and A1 are measured, we always want them to be different. Now you look at this set of equations and you think, well, obviously there's a contradiction here. There's no way you can satisfy this. There's no numerical value assignment to A1, A2, B1, and B2 so that this is satisfied. At least one condition must be wrong, right? Because if A1 is equal B1, B1 is equal A2, A2 is equal B2, so B2 has to be equal to A1. The simple logic, right? So clearly, it is not possible for Eve to satisfy this criterion. At least, your classical intuition will tell you right away that, that at least one condition is not satisfied. So, and if Eve is providing those photons with predetermined polarization, if the numerical values are there, and if Alice and Bob run this test, so the probability of success of satisfying this will be roughly 75%, well, at least, at most 75%, right? Because one condition out of the 4 certainly cannot be satisfied there. So the best, if there are really numerical values assigned to A1, A2, B1, B2, the success is 75%. However, it turns out that you can imagine a situation that physically it is absolutely possible for Alice and Bob to see success rate above 75%. In fact, they can go as far as 85%. And that's kind of shocking, right? So that means that that's certainly not the case that there are numerical values assigned to A1, A2, B1, and B2. Then that also means that that was never the case that Eve prepared this, simulated those numbers, put those numbers into those, whatever, devices or analyzers or even or to photons and gave them to Alice and Bob. So that Feynman actually has a comment on, he goes through this kind of argument or similar argument, and doesn't actually, basically says it's kind of puzzling and interesting, and he doesn't have any good explanations and so on. And I mean, most of us, when we learn for the first time about this, are a little bit puzzled that how is it then possible that we get something that doesn't have predetermined numerical values, because classically you think about the measurement as something that reveals pre-existing property. But in this case, it certainly doesn't look like. And you may just be a bit concerned about this, but there is an interesting way of turning this into something that is useful. I'm not going to talk much about it because but basically the idea is that the fact that there are no numerical values assigned to A1, A2, B1, B2 prior to Alice and Bob measurements, that means that those values were non-existent. The eavesdropper, Eve, couldn't actually put those values. Nobody knows those values because they don't exist. And that can be used for cryptographic communication, where you can run this kind of test for slightly more complicated checking of, you run statistical tests that shows you that if you go about this 75%, then probably there was no eavesdropper on the line, and you can actually distill some secret from the data. But that's sort of like, again, looking at something that looks like a problem at the very beginning and say, well, maybe we can actually take advantage of this and apply it to something interesting. So there was this way of doing this. So basically, this was a situation where, whatever quantum physics took away in form of, from classical security, as I told you, the quantum computers being able to to do efficient factoring can actually break some classical crypto systems. I took you all the way to another quantum phenomenon that can be used for encryption that even quantum computers cannot break. So this, apart from those two topics, what was interesting in this 1981 paper by Feynman was this ability to look at the problem and say, well, maybe it's not a problem, maybe it's an opportunity. And I think this is probably the most interesting general attitude. Whenever you play with something or with a problem, just look at all kind of aspects and look at it from all kind of different perspectives, And then at some point, if you may see that it's many things that look at the very beginning as something that is a nuisance or as an obstacle may actually be useful. If something is very sensitive, don't use it for transmission of data, but use it as a detector or as a sensor, because if it's sensitive, it must be very good, must offer you good sensitivity. So there's always another complementary look at things. So I think I'll stop here, and you didn't interrupt me, so I don't know whether it was clear or not clear. But I'm happy to go into any other direction.